Welcome everyone to this third lecture of Principles of Statistics. In the last lecture, we spoke a bit in detail about the likelihood function and about the likelihood principle. And with this, we constructed the maximum likelihood estimator in a general setting. And today, what we're going to do is to complete that section that we were talking about and talk about this information geometry idea. So with the likelihood principle, I remind you that the principle to apply is essentially to look for the score function, which is the gradient of the likelihood function, and then look for a zero or zeros of that function. So let me motivate something about information theory from looking precisely at the score function. So we can, I remind you from the last lecture that, so recall the following, that the score function that I'm talking about is very simply, or we can write it if we expand out or in terms of the realizations or in terms of the sample. It depends on whether we're looking at it as a random variable or simply as fixed after getting data. So this is the gradient of the logarithm of the PMF or PDF at xi theta. And then I remind you as well that, as I was just saying, the MLE, so the MLE satisfies that it is the zero or a0 of this equation, of this function. And then lastly, I also remind you that the expectation and the theta naught of, in this case, we can write even Sn, is going to be zero, right? So assuming that theta naught is, of course, the true parameter. So let me, at least for the time being, just for this sort of intuition that we're going to get, assume that, so let this guy belong to, so the parameter space be the real number, so we don't need to go to more dimensions to explain what I'm going to explain, and assume that the statistical model is correctly specified and identifiable. Okay, so this correct specification and identifiability, I will assume it from now on, at the very least in this lecture, but generally probably much more than this, without necessarily mentioning it. So it should be, to you now, these concepts should become sort of familiar or natural to sort of think about it, whether I'm assuming this or not, because essentially, if we need to have a true parameter within the model, then that's correct specification. And if we want it to be unique, then we have identifiability. Okay, so these are, that's the very basic sort of idea. Okay, so having this, what I want to look at is the variance of this score function. Okay, and we'll see now in a second why. So the variance, maybe let me use a lowercase for this. So the variance of the Sn at some theta, and this is going to be under the same theta, they coincide. So actually, let me make it a function. So let me put the theta naught, the true one here, and then just make it a function of the theta. And it's simple to check that this is going to be right. So if you look at this, there's this definition of, this expression for the score function, then this is very simply given by the variance under the theta naught of the gradient, right? Of the, in this case, it's not a gradient because we're in one dimension, so it's just a derivative. Yeah. Okay, so the derivative of the log of f, and then we don't need any xi, we just have the capital X with under this measure. Right. Okay. So what we see here then is that essentially the more, if we take the variance, so the variance and the theta naught, so I'm just talking about this guy, theta naught of the derivative. Okay. So the larger this value, essentially the larger that, I should probably, excuse me, sorry, I'm being a bit slow today. So let me actually write it out because I want exactly. I want to fix it at theta naught. Okay, so the larger this value, what's going to happen is that the more sensitivity, so the more variance, essentially what it means is that if the right-hand side is larger, then the left-hand side is larger, so it means that there is more sensitivity, of Sn theta to changes in X, okay, or just equivalently in P theta naught, okay. So that should be clear, right? So, more variance means that you're changing a lot more as the X is changing, right? And so, of course, as well, X is defined through the P theta naught. So when P theta naught changes, then the X will change, and this will affect the score function. Function. Okay. So given that we have more sensitivity, another way of saying this is that as these guys increase, then so does the ability, or our ability, to find theta naught, right? Because if we are very sort of sensitive to changes in theta naught, then therefore we should be able to pick it up sort of easily, right? And so essentially what we are saying is that, the more or the larger this variance, the more information the sample has about theta naught. Okay, so then we've connected this variance, the variance of the score, to the amount of information that a given sample is going to have about the unknown. Okay. Okay, so we're now ready then to introduce a definition. This is definition 5, I believe. So as usual, let's introduce a model. So we have this statistical model for some parameter space, and let it be statistical model for X such that so we want to get the same as, we wish to assume the same as in the observation 2 that we had from the previous lecture. So such that the gradient interchanges with the integral. Okay. So then what we can define is the Fischer information matrix. So the Fischer information matrix is, for the model, and this applies to any theta in the interior of the parameter space, and not including the boundary, and is given by the following. So it's okay, maybe let me just a bit of space. So I theta is going to be the expectation and the theta of the gradient with respect to theta of the log of f at x and theta times its transpose. Okay. Okay, and this, of course, by the way, this is going to be the covariance matrix of the gradient, right? Well, why is that? Well, that's quite simple. So this is by observation 2, because the mean is 0, of the gradient. Okay, so we have that there. Yeah. Okay, and this, of course, I mean, this because this is a covariance matrix, then surely the Fischer information is a positive definite or positive semi-definite matrix. And I mean, in general, it will be positive definite because well, there could be the generic cases, yes. But it will be positive as we would expect that, something that describes information to be, right? Okay, so let me make a remark, because so far I haven't really said anything about the dimension of X. So this actually applies just to general dimension of X and theta as well. And so let's make a remark. So remark, if we have that the sample space is in RD, then this is just a clarification, I guess. Then this guy, the fx theta is actually the joint distribution. Yeah? Is the joint distribution of the coordinates of X. Yeah? Okay, so why am I saying this? Well, that's because in particular we get the following. So we get that if we take X to be y1 to yn, so if this is a sample, this is a sample of y, with y being a real valued random variable, so we have this sort of calligraphic y space in R, so rather than the calligraphic X that we used to have before. Then if this guy is in R, the Fischer information matrix, of Fischer information, what really matters is that it tensorizes. Okay, what does that mean? Well, it just means that if we take the I of theta and try to work out, the value, and this is, by the way, dependent on n observations, so that's a subscript now, and so we write this as usual, as with the definition from above, right? And we get the following, so log, and then now we're going to plug in the joint distribution, which is in this case just a product, and then yi theta times the gradient log f, so we need a product, and so this now from j equal 1 to n, f yj theta, and this, yeah. Okay, so then, it's immediate to see that this is just the sum over I and j from 1 to n of the expectation and the theta of the gradient of log of f y I theta times the gradient with respect to log f y j now theta, and close this. Yeah. So then I will let you just compute this, and you will see that this is just simply n times the expectation and the theta of gradient with respect to theta of the log of f y, only y, no subscript, and this here, the same quantity, just transposed. Okay, so this is just ni of theta. Okay, so this is the tensorization that I mentioned. Yeah, just the fact that we get, and by the way, so what you use here in this calculation is the IIDness plus observation 2. Yeah? So IIDness is, of course, the one of the ingredients, because well, I guess yes. So okay, so do the calculation. So basically, because of the observation 2, you have this mean 0, and then you'll see the IIDness takes you there, essentially. Yeah. Okay. So I guess maybe just to make a little remark. So good. So this is very computationally convenient. But it's but we can also this should be sort of intuitive to you, given that I said that this information is the amount of information that a sample contains about a given parameter. So then what this is saying is, we could even write subscript here as I1. Oh, it's not what I want. I1, right? That's 1. And so what this is saying is that when you have an IID sample, the information that you will have is just n times the information that you would have for a sample of size 1. And that's exactly what one would expect, right? With an IID sample. Okay. All right. So let's move on then and give a second expression for this information matrix, or Fischer information matrix. So for which we need an extra assumption. So it's, the two sort of expressions for the information theory are generally used interchangeably, but the one we're introducing now actually requires a bit more, in terms of assumptions for it to hold. Yeah? Okay, so we say that. So we say that a statistical model is regular, and this is not necessarily totally mainstream definition, but this is a nice way of just referring to it throughout the course. So it's regular if the Hessian, so now this is the second derivative, sorry, the matrix of second derivatives, if the Hessian interchanges with the integral. Okay, so this is the same as before, but now with the second derivatives as well. Yeah? And of course, these require second derivatives of the PMF or PDF with respect to theta. And so, of course, it implies the differentiability that we needed before. Okay, so then let's write proposition. So proposition 1. So assume that we have such model. Assume the statistical model is regular. Okay, so then for all theta in the interior again of our parameter space, what we get is that the Fischer information matrix can be written as the negative expectation and the theta of the Hessian of the log of the PMF or PDF. Okay. Okay, so that's good. So let's just prove it. It's very simple actually to prove this. And I will, sort of give, I will tell you why this is giving us more intuition for the Fischer information matrix. So let's start then just by, writing up the Hessian. That's probably the easiest thing to do here. So we can take the, just maybe a bit more space. So this Hessian, what is this? Well, this is the second derivative of a logarithm. So if you think about it, this should be something like 1 over f x theta Hessian of the f now. And then we have a minus with 1 over f x theta squared, and we'll get here gradients. Yeah? So this Hessian, of course, is with respect to theta, and we get gradients of the f. This transpose. Yeah. Okay, so then it's just a matter of taking the expectation now. So if we take the expectation and the theta, and this is negative expectation, yeah, right, of the left-hand side, this is just simply going to be, well, we could write it simply as the expectation Okay, so let me maybe just do the proof for the continuous random variables, but it's literally just the same with if you go to discrete, then it would be just the same with an infinite sum. And so this is going to be then given by, so we have a minus integral of this 1 over f x theta, and this is over the sample space, and we get here the Hessian theta, and of course we get another f dx, and we're going to get also just the expectation, and actually more than that. So we have, because we're in the interior, then actually we see that the second term is actually the gradient of a log times the transpose. So then what we have here really is just the I. It's just the Fischer information matrix, right? Okay, so then we're almost done. So the first term up here, we see that of course this f will cancel out with this f. And we're always assuming sort of that we're working on where the set where f is distinct from 0, and these kind of things that are sort of basic to assume here. We will sort of be more careful later on when proving more things. But anyway, so what we get is this minus integral over the sample space of the Hessian with respect to theta of the PMF or PDF in this case dx. And so if we can now apply the assumption that we can swap the Hessian by the integral. So that just means that the model is regular. By the way, we're missing this term here. And so then what we'll get is, of course, this plus I theta, and then this will be 0 because this guy is always 1. Yeah. Okay. And so then we've shown what we wanted, right? Okay. So then let's try to get intuition, see what this is telling us. So what we have here then is that the I theta, so the Fischer information matrix, remark, the I theta is the negative expected curvature of the log likelihood, right? Okay, so that should be clear to everyone, because the log likelihood is just so it would be, the sum of these kind of guys, so like the logarithm of the f with all the samples. And then I remind you that x, if x were multidimensional, so just a sample, then this would be the joint distribution, and so you get the log likelihood, and this is the expectation, right? Okay, or the negative expectation of the curvature. So this really what I want to emphasize here is that this is the second derivative, right? So let me maybe draw a little picture. So let's imagine that we have a function, that looks, so I get, rather than having the log likelihood, let me draw the L. So let's imagine that now we have some L that looks something like this. So let's assume that the maximum is here, theta naught. This is L, okay? And then let's compare this to maybe this other picture. This is another L. And then we assume that this L, which is the expectation of in this case, the normalized log likelihood, then we can try to draw, some sort of normalized log likelihood that maybe will look, something like this. And then here we have something like that. And so this would be ln bar. And so what is this telling us? Well, what this is telling us, of course, is that, if we are looking for a parameter here, the theta naught, right? If we're looking for a parameter theta naught, then what situation do we prefer of the two? Well, clearly we prefer the one on the right, right? Because if we are on the left, And, our approximation to L, which is this ln bar, is flat as it looks here. Just, because it is an approximation to the L and the L is very flat around the maximum, then what we have is that we'll make a lot of error, right? While if we are on the skewed version, so on the right, then what we have is, this peak here that will be essentially very, very informative about, even if the approximation is not great, the ln bar, then it will still be informative about where the theta naught can be. Yeah. So then what we've just sort of intuitively gathered is that the more curvature, the more information that X contains about theta naught in this case. Yeah. Okay. So, and this is what is referred to as information geometry, or essentially that the geometry. I mean, the information geometry would be that geometry of the log likelihood that, it's just the geometry of a log likelihood, that will then determine the information of a sample about a given parameter. So it's always relative to the parameter that we are trying to estimate or trying to understand. Yeah? And I guess, yes, so one more thing to say here is that, so the parameter space, we've so far been assuming that it is, within a Euclidean space. And so you're being, as soon as you heard the word geometry, you should be thinking, well, can we extend this somehow to more general geometries? And yes, the answer is yes. And in many occasions, actually, in practice, in many practical applications. So if you think of, for instance, trying to model the shape of a heart or the shape of some organ or something of this kind, so some sort of image reconstruction, for instance, then what you have is that the parameter of interest, is this heart, and this guy is actually going to be living in some sort of manifold. Yeah. So then really what, you can extend all of these ideas to very general manifolds, and and this is a very, very exciting sort of bit about statistics, is that you can mix, a lot of analysis and geometry and this kind of things once you go into sort of more research arenas. Yeah? Okay, so let's now, talk a bit more about this, because we just said that there is some, the geometry somehow will determine the information. But then the question there is, well, fine, so maybe the sample contains a given information, but can we construct an estimator that we sort of exploit all of that information? Is that possible? Or is that really even just the limit as to what you can learn? Or can you learn more? Can you learn less than that? Okay, so then that's where the so-called Cramer-Rao lower bound comes in handy. Yeah? And so this is proposition 2. So proposition 2 is what is called the Cramer-Rao lower bound. And I will do this for p equal 1. Okay, so the generalization to multi-dimension is just immediate, and immediate as in the right. Okay, so then let's take, as usual, a statistical model that is regular, and let's also take an estimator so let this be, particular estimator. So this is going to be any unbiased estimator. So I remind you that unbiased in this case means that if the true parameter says theta, then the expectation of this theta tilde will be theta. And this has to happen for all elements in the sample space. Yeah. Okay, so if we have this, Then, well, this being an estimator based on some sample, on a sample x1 to xn from the model, of course. Then we have the following inequality. We have that the variance of this guy is going to be always lower bounded by 1 over n I theta. Yeah? And this is for all theta in the interior of the Planet space. Yeah? Okay, so of course the quantity in the denominator on the right hand side is the Fischer information for the sample and for this parameter, and on the left hand side we have the variance of the unbiased estimator. That's super important, yeah, that is unbiased. Okay, so what is this inequality telling us? Let's sort of get a bit of interpretation before going into the proof. Well, what it's telling us is that, of course, if the amount of information is very, very small, say if the I is a very small quantity, then what we have here is that what's going to happen is that the variance of the estimator is going to be very large. Okay, so this variance of the estimator is the accuracy basically because of the following. So if we wish to measure the accuracy of our estimator and the theta in the following sense, right? So if we take this quantity, which is the mean squared error, in this case, is going to be, we can add and subtract the expectation of the theta tilde and get that following plus this expectation. Well, in this case, it would be just simply this guy minus theta. This is squared. Okay, so of course, what we see here is that this is the variance. So this is the variance of, this is really just the same guy as there, the variance. And this guy, in this case is going to be 0, of course, because this is unbiased, but otherwise this is what is called the bias. Yeah. And what we get here is that, if we are unbiased, then the variance is exactly the accuracy that we're going to get. And so therefore what the parameter lower bound is telling us is that, this accuracy is determined, or the best accuracy is determined by the information. Yeah? Because this is not really saying that we can attain the optimal quantity. Yeah? In fact, there are examples in which, simple examples of which it's not attained. And what this is really saying when the information is very high is that if there is a lot of information, then you may find an estimator that exploits all of that, yeah? and that it has, as a consequence, very low variance and very high accuracy. Yeah? And now I just want to point out, and this is certainly not examinable, but you will see this, I think, in next term if you attend the mathematics of machine learning, and certainly next year if you stay on for part 3, and it's that you could be thinking, well, if the accuracy is the guy on the left-hand side, and we've taken unbiased estimators, could it be that by taking a biased estimator, one in which the second term is not 0, we can reduce the variance so much that actually the sum is smaller than, had we taken an unbiased estimator? The answer to that is yes. So that is super important in modern statistics and machine learning. And that's, is the realization that we may introduce a bit of bias and still actually have a much better much more accurate estimator. Okay, but I won't say much more about that. We will go back to unbiased or biased estimators in a second, but that's all I want to say about sort of more complicated models, which is essentially what is required for adding this bias. Okay, so let me then go into the proof. So proof, and let's start just simply saying that without loss of generality, we can assume that the variance of this guy is finite, because if it weren't, so if it were infinite, then of course infinity is lower bounded by any quantity. Yeah. Okay. So any real number, of course. So now note the following. So the Cramer-Rao lower bound, maybe let's call it the Cramer-Rao lower bound, is equivalent to just simply looking at the variance of theta of y, and I'll define y in a second, times variance and the theta of z being larger or equal to 1, where y is just our estimator, unbiased estimator, and the z is the gradient. Well, in this case, we're in one dimension, so this is the derivative. Yes, in one dimension. So this is the derivative log of the joint distribution. This would be this guy. Yeah. Okay. Okay, so we have this. And so now, what we want to show then is this product of variances is larger or equal to 1. Well, I mean, product of variances is something that, we know that it comes from some sort of bound. So if you have a covariance between two random variables, then that's, or the square of it is bounded by the product of the variances. Yeah? Or the covariance is bounded by the product of the standard deviations. Yeah? So we know that, or you can, this is just simply also a consequence of Cauchy-Schwarz. So by Cauchy-Schwarz inequality, what we have is that the covariance between y and z is less or equal than, maybe put a square there, is less or equal than the variance y, variance of z. Yeah? So now really what we need to work on is just the left-hand side, yeah? This covariance. So this covariance now is going to be, well, remember that, let me say then, well, recall, maybe, let's say, note that the expectation of z and the theta is 0. Yeah? And so this means, of course, that we can have, well, and so this means that the covariance of yz is just the expectation and the theta of y times z. Yeah? And now what we have is that this expectation of y times z is just simply, and let me do this again for the continuous case, but it's just the same calculations for the discrete. So this is going to be then this theta tilde, and this is for x1 to xn times the derivative with respect to theta of the log of the product xi theta, and this is times, of course, the same product theta, and then of course the xi here. Yeah, maybe let's call it j. Oh, j. Yeah. But then the derivative of the logarithm, and this is, by the way, so this should be xn, and so the derivative of the logarithm will give us, this is the calculation that we've been doing these days all the time. It gives us the derivative of the joint divided by the joint, and so the joints will cancel out, and what we get is simply the integral of this guy times the derivative with respect to theta of the joint. Xi theta dxi. And well, if we can swap, if we have the usual regularity assumptions, then what we get is the derivative with respect to theta of this guy. Well, actually, directly of the expectation and the theta of this theta tilde. Right? And now we can use the unbiasedness. And so what we have is that this is the derivative with respect to theta of theta. So this is a 1. And that's exactly what we were looking for. Okay. Yeah. So now there is a corollary, because really, we use the unbiasedness here, but we don't need to use the unbiasedness, right? At least to get a general result, right? So we have essentially proved the following here. Corollary 1, what we get is that so under the same assumptions as above, of course, so if this is biased, then what we get is that the variance, or its variance, is bounded below now by the derivative of this quantity squared divided by this here. Yeah? Okay, great. So we are nearly done with this. So we have now, so we have now shown this Cramer-Rao lower bound for one dimension. As I said, the multivariate case is also true. And I guess let me introduce something that is, in between the two things. So let me say, a remark, because, for our purposes, we're interested really in sort of one-dimensional cases, just to introduce the whole topic of principles of stats, and then I will just give you the following multivariate version. So multivariate Cramer-Rao lower bound. Usually it's formulated for differentiable I guess, or functionals. Yeah. This goes from the sample space to R. Okay, so this is what I was saying about looking at one-dimensional quantities, but it's really just a functional of the perhaps multi-dimensional parameter. And just to clarify that, this is contained, or this is living in RD with the, maybe P, I think. That's the notation I was using. So P larger or equal to 1. Yeah. Okay, so then what we get is that for all unbiased estimator, I'm going to call this capital Phi tilde, and this is now a function of the data, of course, because it is an estimator, so it's a measurable function of the data, but then also of the parameter of interest, right? And so, by the way, with unbiased in this case, I just mean this guy is going to be just a capital Phi theta, and this is for all theta as well, as usual. Okay, and we need, as in all these results, to be in the interior of the parameter space. So we have for all unbiased estimator this, and for all theta in the interior, we have that the following sort of multivariate version, which is that the variance of this guy and the theta is going to be lower bounded by 1 over n. Then we're going to take the gradient of our functional, transpose it, multiply it by the inverse, by the Fischer information, but the inverse, and multiply again by the gradient of the function. Yeah. Okay, so you will use this in the example sheet, and in fact, let me just give you an example to close the lecture, so that you think about it a bit. This is part of the example sheet, which I'm going to upload today, and so I will upload it to my website, and it may be that I have to upload last year's example sheet, because I'm basically isolating due to Corona, as you know, in a friend's house without Wi-Fi and without LaTeX actually. And so that's a bit of a problem. So I might just upload that one, but it's not going to change anyway. Yeah? So I will try to get it compiled by other people, but otherwise I will just upload last year's. Yeah? Okay, so let me give you this example. So let X be two-dimensional, and this is going to have a normal distribution with some parameter theta. So theta is going to be two-dimensional, of course. Yeah, and this capital sigma is a known covariance matrix, and it's got to be positive definite. Covariance matrix. Okay, so now we go into, and I will take, just for simplicity, n equal 1. So then consider estimating theta 1 when, in the following two cases. One, the first case is that when theta 2 is known, okay, in which case what we have here is that really the dimension of the parameter space is just 1, and we can call the Fischer information matrix, in this case just not a matrix, scalar, I1 theta 1, okay, so let's call it that. And then also try to work out this for theta 2 unknown. So really what you've got now is P equal to, and let me call the Cramer-Rao lower bound I capital phi theta 1. Yeah? So what you will have to show in the example sheet is the following. Is that I1 theta 1 is less or equal than I capital phi theta 1 with equality only when this capital sigma is diagonal. Okay, so the case of capital sigma being diagonal, of course, just means that the x1 and the x2 are independent. And so I let it to you to think about this problem. Why would it be that, that the first case is always going to, have, the information. Let me, sorry, this should be inverse. Yes, okay, so that's, okay, so otherwise I was going to say something wrong. So because of course what you have, so this I on the right, by the way, the I capital phi is not really the information. It's more, like the inverse of the information. And so what this is really saying is that you will have more information when theta 2 is known. So you should think about it, and you should also think about the equality, why it is why does it only hold when you have a diagonal sigma or when the observations are independent. Okay, so I hope you enjoyed this third lecture, and keep up with the good efforts. I've seen many downloads, so that's good. Right, I'll see you again on Friday.